Richard Hennig from Cornell University. Richard got his diploma from the University of Göttingen in '96 and got his PhD in Washington University. We used to be a grad student in the same department, so doing what most of the people are doing here. And then he did a postdoc in Ohio State University, and from 2006 he has been a professor in the Department of Material Science. He switched from physics to material science, and he has always been working closely with experimentalists, and he has been predicting a lot of new materials and new forms of materials that motivated, in my special field, that is field of high pressure physics, motivated a lot of experimental investigations. So today he's going to be talking about computational discovery and design of materials for energy technologies and electronic devices.
Well, thank you very much. Thank you, Shanti, for the introduction and for inviting me, and thank you all for coming. So I'm a physicist by training, so I'm very excited to talk to a physics audience. These days I talk mostly to material scientists, but it's very nice to come back to a physics department. Can everybody hear me in the back also? All right. And I also want to just start right up front telling you if you have any questions about this stuff, or if anything is a little too slow, just speak up, right? I'm always happy to speed things up, slow things down, answer additional questions, etc. Also, I'm happy to answer more questions afterwards about any of the things I've been talking about or other things. I also want to just say right up front to these grad students in the audience that when you graduate, don't look just in physics. Try looking outside. There's a lot of opportunities for physicists in other disciplines like material science, chemical engineering, electrical engineering, etc., to find jobs, to find new opportunities where your physics knowledge actually carries you a long way. So I'm going to talk today about something I've been doing actually for quite some time, but which really started taking off when I started working at Cornell, talking to people there in various experimental efforts, coming up with methods for discovering materials, using computers to discover materials, and to design materials, to modify materials. And the specific applications we have in mind are materials for energy technology, so batteries, photovoltaic applications, or for electronic devices, so coming up with materials which might someday replace silicon in the semiconductor industry. And so the main question I'm going to try to answer for you today is, how can we actually predict the formation of novel compounds, so new materials, and then characterize them, coming up with interesting properties they might have. And specifically, we're looking at how we predict their structure, their composition, and their stability. And we're just using the computer for that. We're not trying to do things experimentally. So the second step in all my efforts is always working with experimental groups, which afterwards try to synthesize these materials. Sometimes that works. We've got a couple examples over the last few years. Sometimes it doesn't, and we'll go back to the drawing board. And I'm going to show you that we can actually predict the formation of compounds and low-temperature phase diagrams by using a combination of quantum mechanical methods, those are so-called density functional methods, and evolutionary or genetic algorithm. We've developed a genetic algorithm code ourselves called GASP, which is available, so if any of you are interested in that, I'm giving you later the link to where you can get more information about that. We apply that code to energy materials for lithium-ion batteries, lithium silicon, and lithium sulfur, to electrode materials. And I show you that we can actually predict for those materials using just the computer what the voltage dependence is for those batteries. We find also a new stable lithium silicon compound, which wasn't known before. And in the second part of my talk, a little bit time permitting, depending how many questions I might get, how fast I am, I'm going to show you how we can use an alternative approach, which is more data mining, looking at similarities between existing materials to predict new two-dimensional single-layer materials, which are in the spirit of like graphene, which many of you heard about it, got the Nobel Prize not that long ago. And I show you that we can discover novel two-dimensional semiconductors which have interesting properties, right kind of band gap, right kind of band alignment to be useful for electronic devices as well as for photocatalytic water splitting. So second slide, I always do that right up front, shows that the work was also, all the work was done by the students in my group. So I list here for the genetic algorithm developed, Will Tipton, he's shown here, did all the development. I also worked with two undergrads, Stuart Wenner and Andrew Sanchez, who was an RU student in my group, developing some components of the algorithm. For the battery materials work, that was actually the application of the genetic algorithm. Will Tipton did that. Clive Beeling, a former postdoc. Kieran Matthew, a grad student. Michael Blonsky, an undergrad student, did work on lithium sulfur. I emphasize the undergrad students here a little bit because I think it's pretty cool that students, when they join a university already in their freshman year, can join a group and do some research on the site and sometimes really get quite far with it. For the single layer materials, my grad student Hulong Zhang, which is in the picture, here he is, and Arunima Singh, here she is, did a lot of the work. Mike Spencer and Ji Wong Park are faculty in electrical engineering and chemistry, which motivated a lot of the work and which also trying to synthesize some of those materials. The lithium beryllium work, and Shanti referred to that as one of the work which we try to motivate experimentals to make some new materials, was actually done in collaboration with the group of Roald Hoffman in chemistry and Neil Ashcroft in physics. And the other topics I'm not going to talk about at all, so I'm not going to list that here, or mention them here. I also need to acknowledge that we get financial support through various centers at Cornell. That's our MERSEC we have at Cornell. We have an energy center funded by DOE. We have a center funded by the King Abdullah University of Science and Technology, and I get funding through the NSF Career Grant. And I'm a computational person, so we use computer time wherever we get our hands on, and the most important resource for us is an NSF Exceed program, formerly known as TerraGrid, and then the New York State Supercomputing Center. So on the next two slides, I tell you a little bit about, first about the various methods I'm using, and then about our overall computational approach. And so the various methods, just like I suspect many of you are experimentalists and some of you are theorists, but it doesn't matter in which field you are. When you look at a problem, you got to first decide what is the right tool for the job you have at hand. And so I'm going to show you here the toolbox for computational scientists, which I show on a diagram where accuracy and computational expense, which scales hand in hand, is shown on the y-axis. So these means more expensive, more accurate. On the x-axis, I show lengths and time scales, and going from very small structures we can calculate, where we can calculate crystal phases, maybe defects. We can look at larger systems, look at transition states between different phases. We can look at dynamics, microstructure, all the way to devices. And then the methods we have go diagonal in that diagram. That means we can do very accurate calculation on very small systems, or we can do very inaccurate calculations on really large systems. So we can simulate a whole bridge using, for example, finite element methods. And that will not have the accuracy of quantum mechanical tools. Today, I'm going to focus mostly on density functional methods. These are quantum mechanical methods which provide the right kind of balance of accuracy and speed. So we can do calculations efficiently, and they most of the time accurate enough, or we know how to fix some of the accuracy issues. I'm showing you also some illustrations just on the side of some of the work we've been doing using various methods on these length scales. This is a trapped clearing spectrum we predict for pentacene and show how that actually agrees quite well with what's experimentally been measured in the Marone group. And I'm just picking that out here today as an example because I had some very interesting discussions with some of the people here about organic electronic materials. So we're focusing on these density functional methods. If anybody's interested in that method itself, I won't spend much time today talking about it, but I'll be happy to give you more material, an introduction, or more information about it if you want to. So let me also outline a little bit our overall approach to materials discovery. So we try to find new materials using computers. And so that's the overall strategy. We do about 3 things in the group. For that, we develop and implement various methods and algorithms. There is a genetic algorithm for structure and phase prediction, GASP, called by my student. We also develop methods which deal with heterogeneous systems. All materials we deal with have surfaces. And so we're always interested in what happens near the surface of a material. In some cases, the surfaces are really dominating the properties, like in the case of 2D materials. It's only surface. In the case of nanocrystals, it's mostly surface. So we develop methods for these materials to figure out what happens if there's a solvent, a liquid, like water, solvating the surface of your nanocrystal or 2D material. And we've implemented methods into density functional methods, and we've developed a method for quantum Monte Carlo method to describe surfaces of materials, liquid on one side, bulk solid on the other side. We also apply these sets of methods and various other methods to a range of material systems, and we categorize them here by their dimensionality. So we look at 3D systems. Those are going to be today the battery electrodes I'm going to talk about, so where we predict what structural will occur in batteries as a function of charging and discharging the electrodes. we're looking at what I call 2.5D materials. So those are surfaces of materials where you've got a bulk on one side and either ligands or something else on the other side. So nanocrystal surfaces is one of our main applications where we've recently showed that by changing the concentration of ligands during synthesis, you can actually tune the shape of the nanoparticle by changing the surface energy from a cubic structure all the way to octahedral structure here. And in 2D, I'm going to show you, it's the second half of my talk, that we look at novel two-dimensional materials which have interesting electronic properties. Resolution here isn't quite high enough. What I'm going to show you later is we take the band gap. We show it as a function of lattice parameter. We show the effective masses in those plots. This is something companies like Intel using for designing their next generation of electronic devices. So I'm going to start out talking about this method, then I'm going to talk a little about batteries and switch over to those 2D materials. So the first thing I want to tell you a little bit more about, give you a little bit of a background about these predictions of materials methods, is I'm going to talk about the energy landscape. When we try to predict new materials, we want to predict materials which are stable, which you can actually make in the lab. So we look at materials which are stable, meaning they got to have the lowest possible free energy. So we're going to turn the problem of materials discovery immediately into an optimization problem. Given a certain number of atoms, certain species for the atoms, what is the lowest free energy I can obtain with that set of atoms? So that's pretty much summarizes that whole field of computational materials discovery. This is a very simple summary, but it turns out that is a very hard problem, which for the last 20, 30 years people have struggled with, and only over the last 10 years have we come up with methods which are efficient enough and computers which are fast enough to really solve that for a variety of material systems. So we need to minimize the free energy. I put free in parentheses here because the first thing I'm going to do is make an approximation and throw out the entropy part. We can add it in later after the fact, and we've often done that. That is, in most cases, sufficient to describe how things change as a function of temperature. So we're going to just look at the energy, or if we're under pressure, we'll look at the enthalpy. So we add the PV term to this. This makes all the calculations a lot simpler because we don't have to worry about vibrational entropy, electronic entropy, configurational entropy, etc. These turn out to be computational, just a little expensive to add on directly in the search. So we need to minimize the energy. And so the next question is, where do we get the energy from? And there's two large classes of computational methods which you can get used to calculate energies. One are empirical methods. So those are things like the Lennard-Jones model and various other variants of it. So Ball and Springs model, Stillinger-Weber for silicon. And these are very powerful methods, but the empirical, and I call them interpolative because they really interpolate between a certain set of fitting data they were optimized for, what the energy is. They are terrible if you apply them to systems they were not optimized for. So for example, for silicon, the Stillinger-Weber potential is one of the simpler potentials for that, does a terrible job, for example, on high pressure phases of silicon. Wouldn't work. So we don't use these interpolative methods in our search because we want methods which really are predictive and extrapolative, which can look at new structures, new materials, and are still reliable. So we're using quantum mechanical, so-called first principles. Chemists sometimes call them ab initio methods. And specifically, we're using density functional method as our workhorse methods because it is that ideal balance of speed and accuracy. All I'm going to say here today, unless you want to hear more, is that we're going to use pseudopotentials and a plane wave basis, and we use specifically the VAST code because it's a very robust implementation of a density functional code. So in our case, in this project, we didn't actually change anything in that code. We just use it more or less as a black box, and we can use various other tools. And then we use that to calculate energies of structures and then develop algorithms which find now structures which have the lowest energy. So let me tell you a little bit about what the energy landscape looks like, what's known in general about energy landscapes, symmetries, etc. of materials. And so the first idea I tell you about is there is something called the Bell-Evans-Pogliani principle you may have heard about, which talks about that you have energy landscapes. Here's an illustration showing a couple of energy minima in your landscape. So this is a conformational space. This is just doing a two-dimensional cut, so it's a very high-dimensional space. And then minima. And these minima correspond to your stable structures. And the Bell-Evans-Pogliani principle tells you that you have highly exothermic chemical reactions, so reactions which take you from one minima to another one which has a lower energy. These transitions typically have low activation barrier. This is an empirical principle. There's a number of counterexamples where that's not the case. But what that means is that when we have found a low energy basin, like maybe this one, it's expected to occur near other low energy basins. So if you're in a good region of phase space, you should search nearby and look at the neighboring minima to see if there's something better around there. These regions in the protein folding community are often called funnels. So you got those minima, and there's other minima nearby, and there's a funnel, and there might be a global minimum nearby. So that's something worthwhile using, so you want to explore the space somewhat local. The other observation about energy landscapes is here shown in a paper by Masson and Doyle, is that when you look at these minima, and you look at the region of attraction, so the size of those basins, there's actually a distribution. The deeper the minima is, the larger, on average, that region was of attraction, that basin of attraction you would have to fall into that minimum. And the reason for that is actually quite straightforward. If you look across all kinds of materials, the kind of bonding you have, ranging from very soft van der Waals bonding to more strong chemical, covalent, ionic, and metallic type bonding, if you look at how the energy changes as a function of change at bond lengths, it's actually not that dramatically different across materials. It might change by maybe a factor 10 or 100 from material to material, but it doesn't span more orders of magnitude than that. That means if I stretch my materials, if I move my atoms around, the energy change is somewhat similar for all these different minima in my configuration space, which means that all these minima are parabolic near the minimum with a similar curvature. And if you think about, you got all these little parabolas in space, and they connect somewhere with these barriers in between. That means if a minimum is very deep, it's more likely to have a very large basin. And that's exactly what Masson and Doyle showed here in their work. They show, as a function of energy scaled to the minimum energy, so -1 is the minimum energy, they show that region, that volume in space, which is the basin of attraction, which you slide down into that minimum. And it follows a pretty straight line for very different kind of models. And the larger the region of attraction is, the lower the energy. That makes our job a lot easier, because what we have to find is that lowest energy structure. And we have a chance in finding it because the region I have to enter and then fall down into that minimum is actually most likely large. I don't have to look for a little rabbit hole in the desert. I'm looking for a large valley. I'm going to show you now a little bit of some of the typical way of illustrating those energy landscapes based on these kind of principles. And here, so the first thing I'm showing is just a simple one-dimensional cut to an energy landscape, just something you sketch out. And the first thing, if you actually ever sketch an energy landscape on the board, you're going to do a pretty decent job. The curvatures you get are indeed somewhat similar for all those minima. This is that, which results in that principle that the deeper the minimum, the larger the basin of attraction on average would be. You don't get very narrow, deep holes typically. But what's a problem with this representation, these 1D cuts, is that they're very misleading, because anybody in the audience can immediately see the minimum is here, right? It's trivial. Why do I need a computer for that? In reality, the configuration space isn't one-dimensional. It's 3n-dimensional, where n is the number of atoms in your unit cell. Scales with the number of atoms. That means even if you have a modest number of atoms in your unit cell, let's say 10, there's a lot of structures. I just talked with Shanti about some which have significantly larger number of atoms in the unit cell. You end up with very high-dimensional spaces. I have a hard time myself, and I know you might be different, thinking about spaces more than 3 dimensions. So figuring out what an energy landscape looks in high dimension is difficult and leads to very complicated structures where finding the minimum is a lot more complicated. Often people draw 2-dimensional images. That's somewhat helpful, but there's actually a similarity between energy landscape and something called Apollonian sphere packings. And I'm showing you here a 2-dimensional and a 3-dimensional version of it. These are packings where you just pack spheres in such a way in n-dimensional space that between large spheres there's always smaller spheres in between. And so these sphere packings have exactly the same property I showed you in the previous slide, where the larger the basin of attraction is, the deeper are those corresponding minima. So it gives you the right kind of distribution, these Apollonian sphere packing. And so what our job in the end is, we're trying to look in n-dimensional space at those kind of sphere packing and find large regions which correspond to deep energy minima. And so here's a 3-dimensional illustration for that. We might try to find one of those large regions. So that's the first thing. I'm giving you a little bit of an idea of what the configuration space looks like. I want to talk a little bit more also about crystal structures, and about that we know more about crystal structure than just the abstract energy landscape kind of picture. Pauling already in 1929 noted that what he calls the rule of parsimony is that's a number of different kinds of constituents, so different kinds of building blocks of crystal tend to be typically quite small. Most of the crystals we're familiar with are built out of little tetrahedra, octahedra, etc. And here's a structure of calcium fluoride. There's a cubic motif, there's a tetrahedral motif, and that builds up the structure. And for most crystal structures, that actually turns out to be true, that you got very limited number of small unit cells which you can use to build up your large unit cell crystal structure. Later also, David Wales showed there's a correlation actually between energy and symmetry, which generally holds, that often low and high energy minima tend to correspond to very symmetrical structure. He showed that specifically for clusters, and here's an illustration for a 55-atom Lennard-Jones cluster, where the lowest energy version of that 55, of taking 55 atoms interacting with the Lennard-Jones potential, turns out to be an icosahedron. And if you look at the highest energy structures, that's somewhat interesting. These are stable structures. You try to come up with the Lennard-Jones potential with structures which are locally stable, so they're minima. And you try to come up with what's the worst you can do. And you end up with these two structures here, which are also having a lot of symmetry. It's immediately visible. That was actually something I found somewhat surprising. But so symmetry helps. So we often have to look for symmetric structures. I'm going to look at crystal structures today. So the symmetry we're talking about are space groups. And so I'm going to show you here now two observations. One is for small organic molecules, and the next one is going to be for inorganic crystal structures. For small organic molecules, there's a database of about 30,000 compounds. And if you look at those 35,000 compounds, out of the 230 space groups we have available, there's only 5 you really have to look for if you want to cover 75% of those materials. So if you want to have a 3 and 4 chance of getting the space group right, you should, for small organic molecules, only need to look at these 5 space groups. You can also tell that these are all somewhat low symmetry space groups in the case of organic crystals. So for inorganic crystals, there's a lot more. There's about 100,000 in the inorganic crystal structure database. And it turns out that about 2/3 of those 100,000 compounds occur in only 24 out of the 230 space groups. So that's still a somewhat small number. And I've actually got a question for you now. Let's think about what kind of crystal structures do you know from your solid state physics class, and which one do you think would occur in the top 24, or would be one of the top ones? So anybody remember some crystal structure? You think, oh, that's got to be really, really common. Cubic, HCP, diamond cubic. Okay, that's good. Two good choices. Any other crystal structures? FCC, BCC. Very good. Anybody else? Rhombohedral. There's a lot of rhombohedral ones, but yeah. I'm not trying to be more specific, but that's good. So let's go with those. FCC, BCC, diamond, HCP, and something rhombohedral. And so here's the table of the top 5. And so the one thing I want to just point out, BCC is not even the top 24. So when you look at how many crystal structures are BCC, out of the 100,000, top 24 of the list are not it, which is somewhat surprising because that's one of the structures we certainly like to teach about. And if I would have looked at economic impact of crystal structures, BCC would have been right on the top together with the diamond structure. Anybody remember why? Steel. There's iron, steel. There you guys, thank you very much. Civilization started to some extent with steel as one of the integral parts of it. I'm teaching material science, I'm also teaching them about steel, so I always like that fact. Good, but it's not actually as common as one might think, despite the fact that's one of the first structures we teach our students. So here's the top 5. PNMA, perovskites actually fall in that category. That's a tetragonal structure. This is a very low symmetry structure. I don't think it's rhombohedral. I think that's monoclinic. P21C, zirconia falls in that category. Here's FCC, copper. And here's a diamond structure. And it's not just a diamond structure, carbon. That space group also has other crystal structure. Here's a Lavis phase in there, etc. But these are the most common ones. You indeed guessed some of them correctly. FCC, diamond, HCP is certainly in the top 24. So what we're learning here is that some space groups are a lot more common than others. So if you want to actually look for making materials prediction, you might really focus on some specific crystal structures first. So that information is helpful. What's also helpful, that we know a lot about the energy landscape based on chemistry. You all had chemistry classes, and you probably remember there's different types of bonds you can figure out by just looking at electronegativities. You know the approximate bond lengths of these systems. You have an idea about coordination numbers. Silicon likes to be fourfold coordinated, etc. And so as a result of this, there's a lot of empirical rules people have come up over the last 60 years, roughly, 70 years by now, of what materials form under what, in what systems. And so Hume-Rothery rules is one of the first one. Lave's rules for intermetallics. Pauling came up with a good rule for ionic materials, which ionic crystal structure occurs as a function of the radii of these ionic elements. I'm showing you here a so-called structure map by David Pettifor, which has the elements on the x and y axis, and these different colored symbols for specific compositions, these are 1-to-1 ratios, show what compounds actually form in these different systems. And then the different colors cluster, and you can immediately see, if you, for example, would look at a compound here where there's no entry right now, you would certainly look at structures which look like what's nearby in there. So this helps you discovering structures. And this is how we discovered structures over the last 50, 60 years or so. And you don't need necessarily a computer for that. You can just look at those tables, etc. I'm going to tell you now a little bit more what happened over the last 20 years, let's say, where we used computers without any experimental input to predict crystal structure. I'm going to tell you at the end about our specific version of the crystal structure search. So the first thing I want to tell you is about an editorial which appeared in the journal Nature in 1988 by John Maddox, which really was kind of, he put a very controversial statement out there, which really got a lot of people started to think about the problem of crystal structure prediction. I'm going to read that to you, because maybe in the back it's hard to see, that one of the continuing scandals in the physical sciences is that it remains in general impossible to predict the structure of even the simplest crystalline solids from a knowledge of their chemical composition. And he goes on and explains it a little bit, and there was an editorial wrote about an article which actually tried to do some of that and was somewhat successful. And it turns out predicting crystal structures is an optimization problem, and if you had any computer science kind of background, computer scientists classify problems after how difficult they are, and the people believe in the community that finding a global minimum of an energy landscape could be an NP-hard problem. I'm not going to tell you what that means because I'm not an expert in that either, but I tell you just what Jeff Erickson at Urbana-Champaign says about an NP-hard problem. If a problem is NP-hard, no one in their right mind should believe that it can be solved in polynomial time. Polynomial time here means if I double the system size I'm interested in, I only go up by some power law in the amount of time I need to spend. So that means it's probably exponentially scaling how hard the problem is. So that's actually what was one of the reasons why many people just kind of sort of stayed away from the problem. It turns out it is indeed a very hard problem. It is indeed exponentially scaling if you do large enough systems. But the prefactor is not as bad as people had thought, and you can actually make progress and do calculations for systems up to 20, 30 atoms in the unit cell relatively efficiently. So I'm also going to tell you that NP-hard problems are not as uncommon as you might think. Here's a paper on the archive by Villetta, Gaming is a hard job, but someone has to do it, which talks about computer games from the 80s like Pac-Man, etc., where it shows that actually turns out to be also NP-hard if you really do the complexity analysis on that. So if you're curious about that, here's the reference, or you can just ask me later also about that. So since that editorial by John Maddox in the journal Nature came out, a lot of people had thought, well, we kind of do come up with some strategies. This is kind of really pushing us a little bit. Let's try it. And so there has been a fair bit of success in recent years with various methods. Historically, we've done things like guessing structures based on symmetry, Pettifor maps, taking the energy, comparing. And I still would recommend to anybody in this field, if you have some good guesses, look at them first. It's just so simple and straightforward. And there's a good chance you might actually be right. People have done things like similar annealings. You heat up your system in the computer, cool it down, see what happens. And that all works in principle, not super efficient. And there's a variety of methods. I'm not going to go through them here in the interest of time. Since then, which have come up, and all have varying success rates in predicting structures. So I'm not trying to advocate any specific method here. I know many of the authors of those methods, and I've seen many applications, so they all do work, and it really depends on the specific system you're interested in, which one might be somewhat more efficient than the others. I'm going to tell you today about two methods a little bit more in detail. One is the random search method, which was first applied by Picard and Needs to crystal structures. It's a very simple method. It's been around for a very long time. And I'm also going to tell you about evolutionary algorithms, which are kind of sort of the random search taken one step further, which was first proposed by Bush in 95 for crystal structures. Again, it's an older method. Woodley et al. In 99 and Artem Organov in 2006 showed that it's a very successful method. This is what we're using. These other methods work in many cases comparably. So if you're interested in those, I'll be happy to tell you more about that later. I want to give you just one overview slide about what these methods in general attempt, showing you that simple one-dimensional energy landscape here again. So many methods are based on kind of what we call molecular dynamics, which is taking a system and try to explore the energy landscape somewhat locally. And they do a very good job, if you have a good starting guess, to find maybe a good local minimum here in the energy landscape. The alternative approaches, which are more Monte Carlo based, they look more globally in your configuration space and try to explore further out what's happening, but they do not do as good of a job in local exploration. And they might find a different minimum, maybe they find this one. None of the methods I showed you on the previous slide, and no optimization method out there actually can guarantee you that you find the global minimum. All you can do is you run them a little longer, you see if something new pops up, and at some point you run either out of computer time or patience, etc., or you found something which is interesting enough, and you work on your publication. So any of the results I show you here today also will have that same constraint. We are not sure if we found global minima, etc. But if we find something interesting, we can tell the experimenters something is happening in that system. Here's a structure which most likely forms. If you do the experiment, you might find something even better than that, but you got a starting guess to work from. So let me tell you about the evolutionary structure searches. And I use the word evolutionary algorithm, genetic algorithm somewhat interchangeably. And these algorithms start with a random search first. So we actually generate a random population of crystal structures. And let me say what I mean by that. To define a crystal structure, what do we need? 3 lattice vectors, and then the position of the atoms in that cell. So we literally take 3 random vectors. We draw their direction and their lengths randomly. We put some constraints on the C over A and B over A ratio to be somewhat realistic. We put some constraints on the angle, because at some point after, there's some symmetries when you go over 120 degrees. That's the same as going to a smaller angle, etc. But they're random. And then we take the random demonstrator again, and then we put atoms randomly in the cell. In our case, we also randomly vary the composition, and we randomly vary how many atoms in the unit cell. We scale the density to be in a reasonable range, because it doesn't make sense to start with something super compressed or super expanded. That's the first step. You end up with a certain number, let's say 20 random structures. We use density functional theory to now relax those structures, to take the forces and stress tensors and minimize the energy. So walk down into the nearest local minimum. So that's called relaxation. We look at the energy, and you could stop there in principle. It turns out that if you do like 50 to 100 random structures at a given composition, there's a good chance you might have actually already found a very good candidate structure. That would be the random search. In the genetic algorithm, you go one step further. You now take some of the better structures from that initial run, from that random run, and try to combine them in such a way that you preserve some of the structural motifs. I'm going to tell you in a second how we do that. So we apply these genetic operators to create the offspring. We make the offspring our new parents. We start over again relaxing, and we cycle that. In our case, we typically have a population of about 20 structures. We might do something like 20 to 50 generations in that cycle to find the ground states of, let's say, a binary phase diagram. And so the most important part of genetic algorithm is this part, the genetic operator. And there's 3 main choices of what you can do that. It's all based on evolutionary biology, the names for those. First thing is selection. Structures with lower energy should reproduce more likely, because there's good structural motifs in them. So we pick more likely the low energy structures. The next one is crossover. We take 2 structures. Here's just 2 structures illustrated, and we slice them up, and we combine them. Illustrated here. We can do that with various ways, rippled or straight cuts, but that's really all it is. 2 crystal structures, and they don't look as pretty as they do here. They're not all simple cubic. There could be some ugly stuff, and then we put them together. You got to do that somewhat carefully, that you don't end up with atoms on top of it, that you end up with something somewhat reasonable. So there's a lot of intuition going into that crossover operation. And then we do mutations. That could be changing a lattice vector, moving some atoms around, changing the species of some atoms, etc. And those are the main operations we do to generate our next generation, and we keep on running. So I can explain that to you in a few minutes, and it actually turns out implementing algorithms like this is quite straightforward. Getting them efficient really means you got to tune kind of how likely you are to do those different operations, what are those, etc. But there's a fair amount of literature these days that you can find information about that. So our code then specifically lets us look for ground states. We also find tons of metastable states, and some of them might be interesting. Some of them you might be able to stabilize. And we can also, what's somewhat unique in our work, look at whole phase diagrams. We don't have to specify the composition. We can say, let's take lithium and silicon, find all the different structures in between. We also have gone to ternary systems. We typically run out of steam with the density functional calculations there somewhat quickly. So we've done most of those work so far just with empirical potentials, just to test our algorithms. But the algorithms at least work. We can search for crystal structures. We can also look for molecular crystals. So instead of putting atoms in there, the little balls on the previous slide, you can put whole little molecules like methane in there and put those in different positions and then calculate the crystal structures. We also modified the code to not just look for crystal structures, but molecules itself, molecules in little clusters. Let's say you have 10 lithium atoms and 5 sulfur atoms. What would they form as a little cluster? Our algorithm works for those as well. And the specific system, lithium-sulfur, is interesting. Sulfur is an energy storage material. Turns out to be so cheap that companies pay you to take it away from them. We have tons of sulfur in the country. And it actually reacts with lithium quite aggressively. It would be a great, very cheap battery material. Turns out that the sulfur, unfortunately, doesn't stay in the electrode. It dissolves in the electrolyte. With forming these little lithium clusters, deposits somewhere else in the battery. The battery only lasts one round. You can't recharge it. And so we're interested in figuring out what are those clusters, what's happening there. That's why we're looking at these lithium-sulfur clusters, also with our code. These methods are really ideally suited for running on these large-scale parallel computers. So if you have 100,000 processors, yeah, we can take advantage of that. Each of the DFT calculation can, let's say, run on 60 to 100 processors, and then we do 100 of them at the same time by just looking at different parts of phase space, different configurations, really run very efficiently. We also interface to many energy codes. Those of you who have done maybe some computational work might know some of those. I'll skip that here. We've publicly released the code last summer. Here's the website, gasp.mse.cornell.edu. If you're interested in that, there's some information on that website, and then you can email us to just get a copy of the code. So one thing which is unique about our work is that we do a composition search. You don't have to tell us what composition you're interested in. We're going to find out which composition do the structures actually occur. And while I say that, I should also just give you one little caveat about all these structure search methods. We'll limit ourselves to somewhat small unit cell structures. That's an input parameter, and for most calculations, we put that to something like 20. 20 atom unit cells, they're quite efficient. Anything much larger than that gets somewhat slow. You can probably go up to 40 if you look at a small composition range, but beyond that gets hard. So what we're doing is we're using the energy as a function of composition to figure out what structures are ground state structures.
So this is zero temperature.
This is a zero temperature diagram. At finite temperature, we can add to each of those points an entropy contribution, T times S, and we can actually calculate some of the entropy contributions reasonably efficient, quite accurate, and then these points would change. And at finite temperature, you also get composition variations by defects, etc. So there would be little parabolas attached to each of those points, and then you could do a construction at finite temperature. The method would still work. The reason why we don't do that usually is that these calculations would take a fair bit of time for each of those data points. So we usually start out figuring out what the low temperature structures are first, and then we add entropy in it if we think it's important. Light elements, it's important. The heavier the element, the less important entropy of this.
Sort of transitions.
Martin-Seg transformations? So there are some transformations, some Martin-Seg transformation, which occur in materials where the high temperature phase is actually mechanically unstable when you cool it. My favorite example I've worked on that is BCC titanium. If you cool BCC titanium at around 1,000 Kelvin, there's unstable phonon modes occurring in BCC, and it collapses into either an HCP or so-called omega structure. If they mechanically unstable at high temperature, there is a chance that we will not find them in our zero temperature search. So that's a problem which I'm very well aware of. I would love to see a method for that. And if somebody comes up with an efficient, and efficient is an important word here, a method of calculating free energy of structures, our method would work on those. It's just that these methods for calculating free energies of these high temperature phases, which are unstable mechanically at low temperature, are not efficient. There are methods, but they just take just as much time as doing the whole search here. So we're not quite there yet. More work needs to be done there. That's a very good point. So composition space search, so what we're doing is we're doing a convex hull construction, because a stable structure means it's got to be on the convex hull, on the lower part of the convex hull of those points. So if you would, for example, look at this structure, this is the lowest energy structure at that composition, but this material would decompose into a mixture of pure silicon here and this lithium silicon 50-50 compound. And then the energy would be corresponding to that point down here. So it would be a two-phase mixture. So any point not on the convex hull is a two-phase mixture in a binary system, could be three-phase mixtures in ternary systems. So we use that as our criterion for stability. The green points are the ones we're looking for. That allows us to illustrate where our structure search is by just plotting points like this, and it allows us immediately to identify how stable is a structure. On the convex hull, stable. The closer it is to the convex hull, the better it is as a candidate for the next generation of structures. So our algorithm works in arbitrary dimensions, so we can look at binary, ternary, quaternary, but we're running out of speed very quickly. We have never tried a quaternary because the DFT calculation would be getting terribly slow. It could be way too many structures. So I'm going to now apply that method to look at two battery systems. I'm going to start with lithium silicon and then just quickly show you some lithium sulfur work. Here's people which actually done most of the work. And I'm going to give you a quick overview about what a lithium-ion battery is. Maybe not all of you remember that. So the typical lithium-ion battery, like you have in your cell phone or in your laptops these days, have an anode and a cathode. The anode is typically graphitic in nature, so here illustrated like little graphene sheets, and the lithium intercalates that, and the lithium is okay sitting in there, but it doesn't really like to sit in there. It rather would sit in the cathode, which is a lithium cobalt oxide, lithium iron phosphide material, another layered material, where the lithium really would like to intercalate. So when you discharge your batteries, when you run your device, the lithium leaves the anode, the graphitic part, diffuses through the electrolyte, and ends up in the cathode. It diffuses as a lithium plus. The electron moves around the outside, does work. Current lithium carbon 6 and lithium cobalt oxide anode and cathode materials have capacities of the order 100 to 300 milliamp hours per gram. So if you take a gram of that anode or cathode, you can store about 100 to 300, 400 milliamp hours per gram. So just to give you a ballpark number. On the second graph here, I'll show you for various cathode materials and for various anode materials what their capacity could be. The scale here you see immediately goes from 0 to 1800 milliamp hours per gram for the cathode, but for the anode we go all the way up to like 4,000 or 5,000 here. And here's a couple of materials choices. Sulfur is a great choice, just based on capacity. Lithium silicon is a great choice. Metallic lithium is a great choice. And they're quite compatible there. And so what we're currently using is down here. So it's good, it powers the devices we have, but if you ever want to run a car on any of those things, we really should go to something which has higher charge capacities than current battery materials. So the first question is, then why in the world are we not doing that? We should be using lithium silicon and lithium sulfur. And the problem is that silicon, when you put into a silicon crystal 4.4 lithium atoms for each of the silicon atom you have in there, that thing swells. And it doesn't swell a little bit, it swells a lot. It swells by a factor of 3 to 4. And if you ever try to put something in a material and have its volume changed by more than 10%, you're going to find that it turns into a nice fine powder. And that's not good for a battery because the electrons won't move anywhere because suddenly it's all broken up. The battery will be dead after the first cycle. So there's actually a way around. People have figured that out over the last decade, that if you go to nano structures for silicon, it doesn't turn into a powder. If you go to nano wires or nano cylinders of silicon, you can actually lithiate them and get about the right amount of lithium in there, 4 lithiums per silicon. It swells, but it doesn't fracture and break up. So there are currently various companies which are making silicon nanowires and using them as a battery electrode material. And with some luck, they can figure out the engineering feats and have commercial batteries, somewhat higher capacity. So here's the work by Park and Kui and co-workers, which showed that these silicon nanowires can have capacities of about 3,000 milliamp hours per gram, about a factor 10 larger than current materials. So that's great. The one thing they also observed, that crystalline silicon during lithiation becomes amorphous. So we were interested also, let's look at that energy landscape for that system. Let's figure out what structures form, what's experimentally known, what do we find in our structure search, and what happens if they were amorphous? How does it affect the energy and the power density, the energy density? So just saying the same thing here. So we look at lithium silicon. This is energy landscape for the known experimental crystal structures. So we just go through the literature, pick them all out. Silicon here, lithium here, and here's the energy landscape. Then we do so first of all I want to say these crystal structures are actually very interesting in themselves. They have very large unit cells, So here's, for example, lithium-12 silicon-7. It's very interesting, intriguing structures. We're not actually trying to discover those structures again. They're large unit cells. They're already known. Our algorithm is probably not very efficient in discovering what's already known, so we don't even try. So we limit ourselves to structures which is less than 20 atoms and try to find, really, can we describe the overall energy landscape somewhat accurately. Here's those, then the lithium-rich side shown on this side. Again, a lot of complicated structures until you reach BCC, room temperature lithium. Here's a table of crystal structure, and you see there's a large number of atoms in some of these crystal structures, so we're not trying. So instead, what we do, we just run with small unit cells, and here's our genetic algorithm results, and here are the low energy structures we find. Here's one which actually turns out to be lower than the convex hull, and a couple which are right on the convex hull. So we're going to focus on those a little bit. Here's the crystal structure. I'm going to show you later a little bit more about that. Let me just skip that for now. We also, so we draw in what the convex hulls for both those points is. And here's actually, we should have drawn the convex hull from here, going all the way down to here. The reason we didn't is we started with amorphous silicon here. The red point is the amorphous structures we generated. We take a chunk of lithium silicon, we heat it up, we quench it down, we heat it up a second time to see if it changes, and here's the data points we find there for what the energy of amorphous lithium silicon is. And we get this curve. What we're doing next is two things. So let me summarize it first. We find one possible new lithium silicon ground state here. It's very close to this one. I'm going to show you that they actually are very closely related. We found a large number of small unit cell structures. Almost all of them are metastable. A couple of them are close to the convex hull. And we have the energies of the amorphous lithium silicon. We're going to use that information to figure out what are the voltages of the lithium silicon electrode are. First, let's look at that new structure. Here's an illustration of that. So you got little silicon dumbbells, and then here's the lithium atoms in between, rows of those atoms. And we looked at the literature for that other structure which was right next to it. And it turns out that these are pretty much the same structure. And von Schneering in 1980 actually did a nice refinement on that material. And he found that at room temperature, these lithium sites aren't fully occupied. It turns out there's about a vacancy concentration of about 1 in 3. There's 1 vacancy per 3 unit cells in that structure. And so this site is only occupied 80%, this is occupied 95%. These are very unusually high vacancy concentrations. So we thought, oh, let's take a look. Why is that high? So we calculate the vacancy formation energies. And I'm not sure if any of you have an idea of what a typical vacancy formation energy is. But for example, in silicon, the energy to create a vacancy is 3 electron volts. In most metals, it ranges from half an electron volt to about 1 electron volt. In this metal, the vacancy formation energy isn't even measured in electron volts. It's milli-electron volts. This is 10 milli-electron volts, 15 milli-electron volts, 50 milli-electron volts. So even at room temperature, we have very large vacancy concentrations in these systems, somewhat unusual, which is actually in this case a good thing, because large vacancy concentrations means the lithium is very mobile in these structures. And so it tells you that lithium could relatively rapidly diffuse in these systems and change the concentration during lithiation or delithiation running the batteries. So we didn't quite find a completely new structure. We found one which was defect-free. At room temperature, it's going to have a lot of defects in it. So the next thing we're doing is looking at the voltages. And so I'm going to show you two curves here. One is Coulombic titration. It's high-temperature experiments, how the voltage in each of those drops corresponds to a phase transformation. If I use the experimental structures at 0 temperature, I get this curve. And you see, within about 50 milli-electron volt on average. And this is due to entropy, the deviation of those about 50 milli-electrons. So that's good enough for experimentalists. If we now look at what our genetic algorithm structures would have given us, the deviation is a little larger, but not terrible. It's probably still within the 50 to 100 milli-electron volt, so still very useful. What that means is we can use the genetic algorithm, and even if we do not find the ground state crystal structures, even if we find just some small unit cell representatives, we still have a good representation of what the energy landscape overall is and what the energy is as a function of composition, what it does. And we can use that to pre-screen potentially new battery materials. What we also find is that the amorphous structures actually do not cause any trouble when it comes to the voltage. They're very similar in the predicted voltage as the ground state crystal structures or our genetic algorithm crystal structures or the Coulombic titration. So in this case, going through amorphous structures rather than crystal structures doesn't cost you any extra energy. So that's useful for the battery community. We also looked at lithium sulfur. There's only one structure forming. We find it in the genetic algorithm. there was a report from 1923, I remember correctly, of a 50-50 compound. It's an interesting paper. It's in German. And it talks about we made some chemistry and we found some material which is colored, I believe, red or something like this. And this is the following recipe we did. It's got to be 50-50 lithium sulfur 50-50. And that's pretty much the end of the paper. So we thought, well, let's look at it. Maybe there is something. And there's something somewhat close to the convex hull, but it isn't quite stable. So we're still not sure if that's what they found. We're currently working with experimentalists trying to go through the lithiation of sulfur and see if they can see some signatures of some 50-50 compound like that, maybe at higher temperature. So again, we can calculate the voltage. Here it turns out to be about 2 volt. This is the cathode. The anode on the previous slide was about 0.3 volt. And so I'm going to show you on the next slide. You can combine the anode and the cathode to make actually a hypothetical battery. And so if you go through the numbers, lithium silicon and lithium sulfur, the capacities, remember for current batteries, like in the laptop here, they're of the order few hundred. We're now in the order 1,000. We combine them. Here's their voltages. We end up with a voltage of 1.6 volt in that case. We end up with a combined charge capacity of 900 and an energy density of 1.5 watt per gram. If you compare that, here's data from Panasonic. The current battery you have in your cell phone has a voltage of 3.6 volt. It's 70 milliamp hour per gram and 230 milliwatt per gram. I got to be honest, we don't include in our estimates the electrolyte, which isn't actually that heavy, and the case. So our numbers should be reduced by something like 30% or so to account for that. But oops, I might have stepped on a cable here. So what we nevertheless learn is there's a lot of room of improvement of current batteries. We can really make batteries a lot more efficient. So if you're interested in working on batteries, there are better materials out there. I want to spend just a few minutes, just give you the flavor of the second part of the talk, really just give you the highlights because I'm running out of time. We're also interested in two-dimensional materials. Again, for similar reasons, we're interested in electronic devices, we're interested in energy storage devices. Let me just, I think the color change has actually something to do that the computer thinks it's night. It's got to be close to sunset here in Utah, or maybe it's on the wrong time zone. That looks better. So we're interested in predicting new two-dimensional materials. Here is an example of an existing two-dimensional material. This is like graphene. This is boron nitride. Molybdenum disulfide, if you've never seen it, these are molybdenum atoms, and these are sulfur tetrahedra stacked around them. These are materials which are currently made and currently being investigated for use as a dielectric, for use as a transistor materials. And there's actually examples that have been shown these work as transistors. We're interested in looking at what other 2D materials are out there. Just because we have those few graphene, boron nitride, zinc oxide, silicon carbide, and molybdenum disulfide doesn't mean that's the whole end of it. We want to really have a full spectrum of them. And so what we did is we looked at materials which have similar 3D crystal structures as boron nitride, which is wurtzite and zinc blend, so the diamond-like structure with atoms. It's either the cubic or hexagonal diamond, and it's just there's 2 atom species in there instead of just the carbon atoms. And so we data mine looking at the crystal structure database, and then we find there's a lot of 3,5 compounds, and they have relatively reasonable formation energies in the 2D form relative to their bulk form, similar to silicon carbide. Silicon carbide has been made, so we think some of these may be able to be made. We look at their dynamic stability by doing phonon spectral calculation. Let me just skip through some of this. But one interesting thing we find is some of these structures are mechanically unstable, just like what you pointed out, shown in the phonon spectrum. And then when you relax them and you come up with alternative ways of making those structures, we come up with a version which isn't hexagonal, which is tetragonal, where you have this is a top view. So instead of hexagons, you get squares, and the side view is they buckled. So this is an image of aluminum phosphide, for example. These are the aluminum atoms, planar, 4-fold coordinated, phosphorus, 4-fold coordinated above and below. So this is a new structure form, and it turns out that some of those have significantly lower formation energies. So I'm showing you here, this is the same data I showed you before, the hexagonal structures, flat or buckled. These are the tetragonal ones. And if you look at the energy scale, we go down all the way to something like 0.15 electron volts. So they're close enough to the 3D crystal structure that they might actually be easily formable in an experiment. What's even more interesting is if you now take those tetragonal materials, and I guess you could do the same thing with the hexagonal materials, and stick them on the right substrate, you could really stabilize the materials. So we take our 2D tetragonal aluminum phosphide, we identify the material which is closely lattice matched, the 100 surface of palladium, stick it on there, the energy drops from 0.3 electron volt per atom to 0.04, to pretty much close to 0. If we then also include van der Waals interaction in our calculation, which are often neglected, we get it that it's actually even more stable than the bulk form. So what we predict is you should be able to grow aluminum phosphide on palladium and get that to be energetically stable. There's a couple other substrates which should do similar things for that case. Then if you look at the electronic properties of that specific material, it has a good band gap, 1.9 electron volt. That's actually a very reasonable band gap for many applications as a semiconductor. That's much better than, for example, boron nitride, which has a band gap of something like 6 electron volt, completely useless as an electronically active material. This may actually be an interesting electronically active material, an alternative to molybdenum disulfide, which has a similar band gap. We also predict that aluminum arsenide has a gap of only 0.8 electron volt, so there's a range of band gaps. Also for the hexagonal materials, here's the band gaps of the 2D hexagonal materials, which we believe on the right substrate, several of them should also be able to stabilize. By the way, this is a diagram you're going to often see when people from the semiconductor industry present their data, their materials choices, band gap versus lattice constant, so you can see immediately which materials you could stack on top of each other, have similar band gaps. And the band gap itself is, of course, important because it tells you a lot of the device properties. And the size of these circles means the effective electron and hole mass. And what it means is you want small circles. Small circles means the electrons on the hole have a small effective mass. It means the material has maybe a higher mobility than the materials which have lower effective masses. So things like gallium arsenide in that 2D form are pretty good. Here's molybdenum disulfide just as a reference. That's what's currently used. So some of these have very similar effective masses, useful materials. With that, I'm actually going to stop. I'm not going to tell you about that we also investigate some of those materials for photocatalytic water splitting to figure out can you use sunlight to split water. I'm going to just show you there's a summary slide that we do indeed find 4 materials which are having the right band alignments with the splitting levels for hydrogen and oxygen evolution of water. And we're currently investigating for these materials what happens if you actually put water into the calculation directly. Remember I told you earlier on that we have a method which describes the solvation, water present in the system, how it's affecting the electronic structure and the stability. That's what's ongoing. This data is only 2 weeks old, so I'm just going to share that with you because we are excited about that. So with that, let me summarize the 2D material search, which I've only given you an overview in the interest of time, is that we believe there actually are a lot more two-dimensional materials out there with the right substrate you could stabilize, synthesize, and which have a lot of potential impact in being useful for the next generation of electronic devices. We'll have to move beyond silicon. There are severe limitations in silicon electronics, which in 5-10 years down the line is going to end the silicon roadmap. And so we can see some of these 2D materials might be great choices for that. Many of those have very interesting electronic properties, good band alignments with various other materials, and they might even be able to use, we might be able to use them for energy conversion applications like photocatalytic water splitting. So with that, let me just flash the first and final slide again, and I'll be happy to answer any question. Thank you very much for your attention.